Okay, let's just jump right in. Picture this. A computer with just 65 processors does a calculation that would take the world's most powerful supercomputer years to finish. No, this isn't science fiction. This really happened in 2025, thanks to Google's quantum AI team. And honestly, it might be one of the biggest turning points in the history of computing. So let's break down exactly how they pulled this off.
It really all boils down to this one number. We're talking about a speed up of roughly 13,000 times. You heard that right. In a direct, head-to-head challenge, Google's new quantum processor ran a complex, real-world physics simulation, 13,000 times faster than Frontier, which is, the fastest supercomputer on the planet.
So that brings us to the big question, right? The real mystery we're going to unpack here. How? How can a tiny machine with just 65 processing units, we call them qubits, just completely blow away a supercomputer that has millions of them? Well, it turns out the answer isn't about raw power. It's a story all about quality over quantity. All right, Section 1, a new quantum era. You see, to really get this, you have to understand that 2025 was the year quantum computing kind of grew up. It went from being this theoretical what-if toy in a physics lab to a legitimate, powerful tool that can start solving actual problems. So let's dig in. Okay, let's get to the hardware. Section 2. Meet the Willow processor. The absolute star of this whole story is Google's brand new processor. It's a superconducting chip, and its code name is Willow. Now, you might have heard of its predecessor, Sycamore, which made waves a few years back. But Willow was built on a completely different philosophy. So yeah, Willow has 105 qubits, which is almost double what Sycamore had. But honestly, that's not the important part. The real game changer here is the shift in focus. It's not about just cramming in more qubits, it's about making better qubits. Every single thing about this chip, from its physical design to its ridiculously high accuracy, which they call gate fidelity, it's all been optimized for one single crucial purpose: fighting errors.
And that quote right there, it really gets to the absolute heart of the challenge in quantum computing. You have to understand, qubits are, well, they're incredibly fragile. They're nothing like the solid, dependable ones and zeros in your phone or laptop. A qubit's delicate quantum state can be completely wiped out by the slightest change in temperature, or even a tiny vibration. For decades, this error problem has been the brick wall holding the entire field back.
Which brings us to the most important part of the story: conquering quantum errors. So, how did Google build what's basically a shield against this chaos? Well, they realized they couldn't just make a single qubit perfect. Instead, they came up with an ingenious system where groups of qubits could work together to protect each other. Let's take a look at their secret weapon.
And that secret weapon is something called a logical qubit. Now, the concept is brilliant. Instead of relying on one fragile physical qubit, you create a team of them. Imagine a whole group of these noisy, error-prone qubits all working together, constantly checking each other's work. By arranging them in a special grid, they create a single, super-stable unit that can literally detect and fix its own mistakes in real time. It's like a self-healing computer.
And this is where the magic really happens. Take a look at this table. It shows what happens as you make that team of qubits bigger. With a small 3x3 grid, you get a certain number of errors. But look what happens when you scale up to a 5x5 grid. The error rate gets cut in half. Then you go to a 7x7 grid, and it drops by a factor of 4. The error rate doesn't just go down, it drops exponentially. This was the breakthrough they were searching for. Proof that for the first time, making the system bigger actually made it stronger.
And that's what's known as the below-threshold milestone. This is a huge deal. Think about it. For the entire history of quantum computing, making a machine bigger just meant it had more ways to fail. It got more fragile, more chaotic. This is the first time that adding more qubits actually made the computer more powerful and more reliable. It's the tipping point where the self-healing system finally became stronger than the errors attacking it.
Of course, for this self-healing to actually work, it has to be mind-bogglingly fast. And it is. The Willow system performs 909,000 error correction cycles. Not per minute, not per hour, every single second. That's fast enough to catch and fix errors on the fly, before they can spread and ruin the whole calculation. Okay, so now they have this stable, self-correcting quantum computer. Section 4 is about how they proved it, the quantum echoes breakthrough. It was time to put it to the test with a really demanding algorithm. And this wasn't just some abstract benchmark. This was a complex simulation with real applications in science, something specifically chosen to prove, without a doubt, a true quantum advantage.
The experiment is called the quantum scope algorithm.
It's a really clever way to see how information scrambles inside a quantum system. Here's how it works in 4 steps. First, you send a signal in and let the system just do its thing. Second, you pick out one single qubit and give it the tiniest little push. Then, and this is the cool part, you precisely reverse everything you just did, like rewinding a tape. Finally, you listen for the echo of that signal to come back, and that echo tells you everything about how that one tiny nudge created ripples through the entire quantum system. It's like seeing the butterfly effect in action at the quantum level.
And here it is, the result. This is what it all comes down to. To run that exact 65-qubit simulation, Google's Willow processor took about 2.1 hours. Okay? Now, how long would it take Frontier, the fastest supercomputer in the world, to do the same calculation? An estimated 3.2 times years. Hours versus years. Just let that sink in for a second.
But here's something that's almost as important as the speed. The result is quantum verifiable. What that means is, unlike some of the early claims of quantum advantage that were kind of fuzzy and hard to double-check, this one is solid. It's precise. Another team with a similar quantum computer could run the same experiment and get the exact same answer. That's a massive step. It's what turns it from a cool experiment into a trustworthy scientific instrument.
So the big question is, where do we go from here? We've proven the power is real. Now what? Well, this isn't about just doing cool science experiments forever. Google has a very clear, very practical roadmap to get from where we are today to actually using this power in the real world.
They've broken it down into 5 stages. Stage 1, discovering the algorithms. Well, we've been doing that for decades. This experiment, Quantum Echoes, puts us squarely in Stage 2, finally proving that quantum computers can beat the best classical computers on a meaningful problem. So now the hard work really starts. That's Stage 3, which is all about finding real-world problems that these quantum solutions can actually solve. After that, it's about engineering and actually deploying it for people to use in Stages 4 and 5.
So what are we actually talking about here? What are the first home runs we might hit with this technology? Well, think about things like designing brand new types of batteries that don't need rare materials like cobalt. Or what about in medicine? Being able to simulate exactly how a new drug will interact with the body, potentially creating cures in a fraction of the time. Or even creating totally new materials from scratch, because we can finally understand how molecules really work. These are the kinds of massive, world-changing problems we're talking about.
Now, of course, Google isn't the only player in this game. Their biggest competitor, IBM, is taking a totally different approach. They're focused on just building bigger and bigger machines with more qubits, like their 1,121-qubit Condor chip, and getting them into the hands of businesses through the cloud. You could say it's a classic tortoise versus the hare situation. Google is betting on perfecting error correction first, quality. IBM is betting on massive scale, quantity. It's going to be fascinating to see which strategy pays off.
But at the end of the day, this quote really captures why this is such a big deal. The whole conversation around quantum computing has fundamentally shifted. We're moving out of the phase of just talking about what a quantum computer might be able to do someday and into an era where we can point to what it is doing right now. These aren't just theories anymore. They're real tools doing real work that is simply impossible for any other computer on the planet.
So, to wrap things up, I want to leave you with a question to think about. We've seen that the 2 biggest roadblocks, errors and verification, are starting to fall. The path forward is clearer than it's ever been. So, which industry do you think gets there first? Where will we see the first true transformation from this incredible new power? Will it be medicine, new materials, or maybe clean energy? What do you think?